Hello, everybody. Welcome to Houdini Hangout. It is the 16th of January, and we're continuing to go through the Joy of Vex. Thanks so much for joining the stream. Hopefully, you've been able to watch some of the previous streams up to this point. Obviously, these talks kind of ramp up in complexity and kind of, just the in-depth nature of them overall. We've got some interesting stuff to talk about today, some arrays, for each loops, and creating geometry through Vex. So really hoping that this will be very informative for you, that that you'll be able to get a real lot out of this. I think there's some really key points in here. I think once you start getting into some of the for loops and things like that, for each loops, you start to get into the real power of what you can actually do through programming in Houdini. So really excited to be able to start to get into some of these things, and kind of the examples just get more and more in depth, I think, and more exciting kind of as you go through it. So I remember a couple people mentioned that they were kind of starting to run into some trouble around this time in kind of the going through on their own. So hopefully we can maybe make some headway for those people, and get you over that hump into like really understanding what's going on with some of these core concepts in Vex. Obviously, at the end of 20 days, you're not going to be, or 20 lessons, however you want to look at it, you're not going to be have mastered this programming language, but it certainly is going to be something that gets you off to a really good start in understanding it. So so just a real quick, introduction. Like if you have anything you'd like to comment on the stream, happy to have you drop that in the chat. This certainly is a conversation, and not just me here talking to you guys the whole time. I'd love to have some back and forth, be able to understand and explain things better if there's some something that isn't being understood super well, and just be able to have a conversation, right? So I dropped a link in the chat, houdinihangout.com for our Discord invite if you'd like to go there and have more conversation after, outside of these live streaming times. And I'm going to also put in the chat the link. Oh, sorry. That's not the link. My bad. Sorry about that. We got something crazy going on there. Sorry, my bad. All right, let's do this a little bit more. There we go. That's the link to where we're starting. We're on, if you go to the cgwiki and Joy of Vex, day 12, that's where we're starting. So, I guess really without any further ado, let's jump in and we'll start to kind of talk through some of these points here. So, all right. Hey Matt, yeah, good. Glad to have you with us. If we run into any major snags or whatever, I know you're there to bail me out. Hey KG, nice to have you on the stream as well. Hello. Cool. All right, so day 12, we're going to start talking about arrays. And so arrays are lists of values, right? That's kind of what they are by, definition. So let's first, before we get into arrays, just kind of make a short kind of recap of what vectors are, and we'll kind of go from there into how we work with arrays. So first of all, let's just drop down a point wrangle here, and we'll just add that onto this grid. This isn't going to be super important right now, but we can at least use this to kind of see what's happening. So, all right, so let's first define a vector variable. So we'll do vector, we'll call it my vector. And let's just use the curly bracket method that we've been using here. In this case, we'll do 3 numbers inside of there, all separated by commas, and that'll define the 3 components of our vector. So here we're just going to do 1, 2, 3. Just like this, and do a semicolon. So that's just defining, a vector, right? A vector variable. But if we want to define a vector attribute, we do that slightly differently, right? Attributes, we remember, use the at kind of prefix. But what we need to do to kind of make sure that Houdini knows that we're making a vector attribute is call for the type vector, right? So here we can do v at a, so we're going to make an attribute called a, and it is going to be a vector. And so now we're going to use the same curly brackets and say 10, 12, 100, right? Close those curly brackets. And now if we control enter, we'll see that we have an attribute called a that is 3 floats, right? So it's a vector. And we've written that just kind of explicitly using our curly brackets, right? So we can then now we have this attribute saved to all of our points, right? And so we can read any component from that that we might want. So let's say we wanted to make another variable from this, but just take one of those components. So what we could do is we could say float foo equals at a dot x, right? And this is going to return 10, right? Because that's going to take our first component, the x component of our a vector. You can also do this using an integer notation, basically saying what the ID of the component is, right? So let's say we wanted to instead do float foo is a, and then we're going to use a square bracket here to say index 2 of that, right? And that's going to return 100. Now, let's just look at this a little bit more closely. We know that we can we can read in our variables this way, and we can also just write a random variable as well. So let's just do this, say at foo equals a2, right? So now we can see that foo is equal to a2 here. And if we wanted to go back to the previous example and say a.x we'll set foo equal to that, now we can see, sure enough, a.x, which is the first component, xyz, and that is going to be 10. So we're pulling 10 out of that and writing that to foo. So we can see how we can kind of manipulate these vectors, whether we're using this kind of XYZ or RGB. You can use that as well. You could say A.R or A.B or whatever to get the last one. So there's a lot of different ways that we can kind of talk about getting these vector components, right? And that's all well and good, right? But what if we have a situation where we have more than 3 numbers, 3 elements in this array, right? So that's when we start to use our array attributes and our array variables to start storing data. So we'll just scroll down a little bit here. We can see how we're going to start to define an array. So it's really very similar to what we've done before, right? So let's just here say float, and then we'll say my float array, and we'll make some square brackets there. We're gonna set this equal to, and we're gonna say use the same method with the curly brackets, but say 1, 2, 3, 4, and 5, just like that, and then a semicolon. And we don't have any syntax errors or anything like that. So it looks like we've written that properly, right? So we can do this with floats, right? We can also do this with vectors, right? So what we could do here is we could say vector, my vector array, like that, and put our square brackets after it to say that this is going to be a vector array. And then we'll set this equal to, and we're going to use these 3 vectors inside of our array, right? So we're storing 9 digits, but they're in groups of 3 vectors, right? So here now we can put one open curly bracket and then another, because we're going to store 1, 2, and 3 in the first vector. So we close that. There's our first vector. Then we put a column, open up our second curly bracket, and say 4, 5, 6, close that. And then we'll say 7, 8, 9, like that. And we will then close the last curly bracket and put a semicolon there. That should hopefully evaluate properly. Sure enough, looks like it did. So there we're storing 3 different vectors in an array, right? So if we called back one of those indices from that array, you would get a vector back instead of a float, right? So if we wanted to write one of these to an attribute, I'm just going to get rid of this so that we have a little bit less in our geometry spreadsheet down here. So we'll do that. We also don't need to be writing these anymore. So we'll do this just to clean it up a little bit so we can read this nice and clean. So now let's write an array to an attribute, right? So what we need to do is we need to say F for float, and we need to put our square brackets after the float. So now we're saying we're doing a float array, and we're calling it A. So that is kind of our syntax for writing a name. You have whatever type, then square brackets, then the at, and then the name of the attribute, like this. So now we're going to create an array called A, and we're going to do the same thing we did before. 1, 2, 3, 4, and 5, like that. Semicolon, and hit enter. Now something actually is going to pop into the geometry spreadsheet because we're defining an attribute, right? This stuff is going to be persistent through our network until we delete it or do something else that gets rid of it. But now we have this nice persistent attribute that we can see has 1, 2, 3, 4, and 5 inside of it. So if we were to call A and then 0, we'd be able to pull out 1 from that. And just to note here too, you can tell this is a float because it has a decimal after it, right? It has a fractional component to it. If we wanted to do this slightly different, we could set it as integer by saying I, like that, and now this is an integer array, right? So just something to keep in mind, that we're going to start getting more into the kind of the habit of specifically saying what these attributes are that we're writing, just because it's going to make our code cleaner and it's going to cause less confusion within Vex down the line. So it's a good thing to kind of keep in mind. So, all right, cool. So now let's do the same thing with a vector. I'm just going to make this a little smaller here. And what we can do is we can say v at vex like this. Oops, I actually did the exact problem there. I just mistyped. So we need to do our brackets there, right? So we'll do v at vex equals, and then we'll do the same thing we did before. In fact, just so I don't have to, write all that out again, I'm just going to copy and paste this. It's going to be the same thing, right? So there's our vector array that we're going to write. And if we look here, we can see that this is slightly different the way that it's written in the geometry spreadsheet. It's actually maybe a little bit clearer to see, but here we can see that our entire array is within square brackets and each of our vectors are within these regular brackets here. So we have 1, 2, 3, comma, 4, 5, 6, comma, 7, 8, 9. So we have 3 vectors in there, right? So let's say we wanted to retrieve some of those attributes. I kind of mentioned this a little bit, but what you're going to do is use what we did before with the index, right? That's going to be the way that we can call these back, right? Because we can't do XYZ or whatever, because what if you wanted to go to the 4th, right? That's not going to make sense. So in this case, we're going to just use integers in order to call that back. So first you'll see here that we're going to, let's write the third index, which is 2, right? It starts at 0, then goes to 1, then goes to 2. So that's the third index. So we'll write that into an attribute called B. So let's do that. So we'll do at B equals F, and then we'll do the bracket at A, and we'll do 2, just like that, right? And so now we should have this attribute called B that is just pulling out the third component of this array here, the third part of this array. And let's also do that for one of the vectors. So here we'll say v at C is equal to v bracket at vex, right? Like that. And we're going to pull out the second one, which is index 1. All right, and we'll do that. And now we should have a C attribute here that is 4, 5, and 6. And if we just open this up a little bit more, we can see that the second index here is 4, 5, 6. So we've pulled out that vector and written it to C. So that is all hopefully pretty straightforward. The real difference there that we're going to be seeing is those brackets that we're either writing at the end of the name of a variable or right at the beginning after we declare whatever type it is, like a float or a vector. When we do f brackets a at a, or v brackets at vex, that is going to be the way that we define an array in our attributes. So it's a little bit different syntax there for each of those, but hopefully that doesn't kind of throw you too far as kind of this new way of understanding. You can write a bunch of kind of a comma separated list in an attribute or a variable. So these are really powerful, and you're going to see in a little bit why these can be so helpful. But these are ways that you can do things over a lot of different data really quickly within Vex. So what the last thing we kind of need to talk about here is that if you want to do something in other than numbers, in this case we've used all digits up here, and if we want to do something different, we need to use some functions in order to properly set up vectors and arrays with using variables. So if we have a variable in our somewhere in our code that we want to set into a vector, we need to use a function in order to do that. So let's just take this out of here since we're kind of done with what we're doing there. And let's just kind of work through this next bit of code here. So we're just going to make a float a, and we're going to set this equal to 42, right? So now we have a that we can work with. So what you might think to do is do something like this: vector myvec, like mistyping there, myvec equals, and then if we try to do this, the curly bracket thing, like a to 3, like this, right? That's going to error out. We're going to get a nasty error, and we're going to try to figure out what this is, and syntax error, all this unexpected identifier and things like that. So this is going to error out, right? But what we can do is use this set function. So instead we're going to say set. I'm going to change this from curly brackets to regular brackets, change both of them, make sure I do that. So now if we use the set function, we're going to be good. That's going to work. And just so we can see that, I'm going to say, we'll just set an attribute called a, and this is going to be a vector. Oops, sorry. It's going to be vector a, and we're going to set this equal to myvec. So now we can actually read this out, and sure enough, it's 42, then 2, then 3, right? Because we have a is set to 42, so we're saying 42, 2, 3 here. So that's working. Everything's going great there. The other thing we could do is set this right off the bat, right? We could just take this line out. We could take our set right here, right? Cut this out, and we could just write it just like that as well. So we don't have to do that in 2 separate steps. We could do that all in one, and it's going to give us exactly the same thing. Nothing changed at all there, right? So that either one of those are correct ways of going about that. Kind of depends on maybe how exactly you're setting up your code and how it's progressing, but kind of how you have your logic going through. But just something to keep in mind that that's how you would do that. And then similarly, if we wanted to put that into an array, we might try something like this, right? The same thing, float my array like this, put our brackets, set that equal to a, 2, 3, 4, 5, something like this, right? And I'm sure you can imagine, like before, it's going to error. It's going to give us that same syntax error and say, no, this isn't right. So what we need to do is set it to array, and then make sure we're using regular brackets here. So we'll do that. And now we should have a nice array that's formed properly, right? And again, we could do this, set an array from that in a couple different ways, right? We could use that variable like we did before, or we could just explicitly set it just like this. So we could say f at my array, if I can type right, equals, and then we can just cut and paste this right here, right? So this will still work. We'll paste it down here and get rid of this guy. And there we go. Now we have an array. My array is 42, 2, 3, 4, 5, right? Just like we would expect from that. So just to keep that in mind, when you want to create a vector with a variable in it somewhere, you use set. Maybe you want to make one of all variables. You need to use set. If you want to make an array of with one variable or all variables, you need to use the array. So set is for vectors. Array is for creating longer arrays. So there we go. So that's kind of gives you a little sense for how to work with this. So, all right, so we did that. So now let's go back to some maybe more practical examples to actually work through how this might look. So we're going to be using our grid here. So I'm just going to zoom in a little bit. And well, let me just pause there and just mention that if you have any questions, feel free to drop them in chat. I'll take a look at those, and if we need to go back and clarify anything, happy to do that. So yeah, please always feel free to be able to drop question or comment in the chat. Just if you're not clear on something, that's probably means someone else isn't. So it'd be great to hear. There's no dumb questions or no dumb comments here. So all right. So let's do a more practical examples, like one that we've done before. So we're going to do kind of the Voronoi pattern that we did before. So we're going to do a scatter here, get some points, and we're only going to do 6. Do that. Ours is going to look a little different than the way Matt's did in his example. I think there's just some calculations that are a little different between this version of Houdini and the one that he had used it on. Sometimes some of the functions get changed slightly and it just randomizes slightly differently. So you'll probably notice there's a little bit different here. I'll also use a color just to give these points some random colors here. I'm just going to say random. We could change the seed if we wanted to. Now we can see that they're colored here. I'm also going to go into my geometry here and change the point size to be quite a bit bigger so we can see these points and their colors better. And I'm just going to grab kind of a randomized color here. Maybe, I don't know. That looks good. Looks varied enough to be interesting. Okay. So we've got our point wrangle here. I'm going to just say JOV day 12 down there. So we're nice and clear as to what we're doing here. So the grid's coming in input 1 and these scatter points are coming in 2, just like previous examples that we've done. So here's our wrangle, and I'm just going to get rid of this stuff and we're going to go into a more practical example now. Cool. Okay, so we're going to be talking about the near points function. And what this does is very similar to near point, where it finds the closest point on the geometry that you're specifying. However, we can store more points than just one into an array and then use that to be able to play around with and do some interesting things with. So so this is going to be a more powerful version of near point. Not to say that you wouldn't use near point ever. That's certainly not the case, because sometimes you want just that one integer number to be able to use quickly without having to try to pull out an element from an array. This is just kind of a different way where we might want to look at more than one point, and we can store that all into one variable in this case. So let's start working through this code here. So we're going to make a point attribute. So we're going to make an integer attribute called PT, and we're going to use near point to get this, right? So let's do this with 1 and at P, because we're going to look it up by position. Then we're going to make a vector called col, and we're going to grab the color from that, right? So we're going to use a point function on input 2, and we're going to have it return the CD, the color of that, based on whatever the near point is. So we're going to use, this is looking it up based on whatever the near point is for this particular point on the geometry. Because remember, this is running over all of the points in our geometry. So each point, it runs this code, right? And whatever the near point is for that specific point on this grid, it returns that, right? And then at the end, just a simple writing of COL to our color, just like that. And we can see here that this is working kind of exactly how we'd expect it. We're getting this Voronoi pattern. As we change the way that this scatters, it'll change it around a little bit. We can see that these will kind of warp and change depending on how, kind of spread out they are. We could add some more relaxed iterations, less. That's basically just adjusting how far the points are kind of getting pushed apart. But anyways, we've got these colored sections here. So let's extend this a little bit in order to, basically get the distance to the point, store that as an attribute. I'm sorry, as a variable. And we're going to multiply the color by that. And that's going to be able to kind of make a smooth like disk of color that'll kind of go out from each of those points. So we're going to work through this here and kind of expand on this a little bit. So we have color. Let's also get the positions. We're going to do vector pause like that. And we're going to go for a point function. And we're going to say the second input, we're going to get the position, so P, and we're going to use the point again, which just to remind you is the nearest point on our geometry. I forgot a parentheses there, so let's do that. Okay, cool. So now we've got pause and call. So those are our position and our color. And so now let's calculate the distance, right, from our current point to this, the whatever the near point is, which we have the position stored as pause. So let's do float d, and we're going to set this equal to the distance. And that's going to be between at p. Okay. Oh, I hit that by accident. Sorry, at p. And then we're going to put pause as the second one there. Great. All right. So now we have this float d, right? That's storing the distance from our current point position that we're looping through in this wrangle and the position of the closest point. So now we have a distance that we can use. So here we're going to use a fit function. So d is equal to fit. So we're going to fit d to something. And we're going to say between 0 and a float channel here, which you can just use ch for because it defaults to a float. We'll do radius. And then what we're going to do, so we're taking, we're fitting the, however far along this distance, right? So we're kind of using this as like to clamp the incoming, right? These are the incoming attributes. So we're looking between 0 and this radius value that we're going to be able to change. And we're going to invert this and set it from then to 1 and 0. So we're taking 0 to whatever and setting that to 1 to 0. So we're kind of flipping those across. And let's put a semicolon there. And then finally, let's set d equals to the clamp of d. And we're just going to make sure that it stays between 0 and 1 here. And then down on our last line, instead of just doing col, we're going to multiply that times d, right? And so I forgot something here. So we have a little bit of debugging to do here. I must have mistyped something. So we have an unexpected semicolon. It was expecting a parentheses. So let's do that. And I think that should clear this up for us. And so right now we still have an error because I, again, missed something here. So we're going to do this, and that should clean that up. This actually didn't need another parentheses there. So now we're good. So sometimes, you have to kind of look at your code to see what you did wrong. I mistyped there and didn't close my bracket on that channel. So there we go. So this is just resolving to black because we don't have our radius set here. So we're going to add in that channel. And now as we go further and further here, we'll see that these circles kind of start to fill in. However, when we get to the edges of those cells, it can't blend past those, right? We're just multiplying that times this distance function, right? So we need to be able to start to look beyond the borders of that near point and start to kind of blend using up more than one point value. If you're used to doing things like attribute transfers and things like that, a lot of times there's like a radius for how far you're going to be looking to transfer that attribute. And you can also blend if you look at more than one point. So that's kind of what we're doing here now. So we're kind of doing the programming of that kind of a concept where we're taking attributes based on, you know, a radius and fall off and things like that. So let's now take this function, which is just using near point, and switch it over to near points. And the difference there is going to be that instead of just giving us an integer, it's going to give us a array of integers that we can use, you know, to adjust how this is working. So, okay, so here's the next block of code that we're going to work through here. So let's first change this over to near points. So here, instead of int point, let's do points, and we'll do a bracket there. And so we're going to change this to near points, right? And we're still going to be going on the second geometry. We're still going to be using at p, but now we're going to say 40 here. And basically what this is saying is that we're giving it a distance to search within. So within 40 units. Okay. So that's the third, it's angry at me because I clicked off of it, but so we're looking within 40 units of whatever this point position is that we're searching from, the current point position. So, all right, so now we have an array of these near points, right? So we need to then take one of those points to be able to do all this code on, right? Because this needs to just know one point here. So what we're going to do is use what the bracket index method that we did before to pull out one of those points. So here we're going to say int pt equals, and we're going to call points and put 0 in brackets there. Now, if we hit enter, we should be good. And so now this is working. This is doing the same thing kind of it was doing before. It really hasn't changed at all. So what we need to do is actually run it on the next closest point as well. So what we need to do next is we're going to do two things. We're going to tidy up our attribute calls, right? Because, our variable calls, because what we can't just do here is take this block of code and copy and paste it again, because this is going to freak it out, because these are already called. We don't need to have these purple, you know, kind of type calls to say integer point, vector position, you know, those have already been stated. So we don't need to do that twice. And in fact, we can do it once for both and make our code even cleaner. So that's what we're going to do in this next section here. So what we'll do is we'll leave this here, and we're going to make a little block at the top to kind of declare our variables, right? So we're going to say vector. So we're going to be making two of them, pos and col, and we'll put a semicolon there. So you can see I used a comma to denote the two different ones there. We're going to make an integer array called points, because we're going to need that. And then we're going to make an integer attribute called point. And finally, we're going to make a float called d. So these are just empty declared variables. They're not doing anything yet. They don't store any data. But now we can use those to kind of clean the rest of our code. We don't have to have all of these declarations all around in our code. So here we already have points, so we don't need to do this. So we can get rid of this int, and we can also actually get rid of this these brackets, because points, we already know it's going to be an array. So we can just say now points is going to be equal to near points. So that's great. We're looking within 40 units of that. Secondly, let's do at cd equals 0, just to kind of initialize, so no, 0, just to make sure that we have our color set to black. So that's going to set all of the components of that color vector to 0. Then we can go down here and just clean these purple declarations out. We don't need that, don't need that. Oops, don't want to delete 2 lines. Oh man, that's too bad. I'll have to do that again. All right, so we're just going to get rid of all of these, right? So here we can see we're doing point equals points, right? The position is the same thing, 0.1, p, and point. Color is getting the second input, getting the color from that, and using the current near point. And then d is the distance, just like we had before. All of this is going to be exactly the same. We're still clamping it. Now, the only difference here is that we're going to say cd plus equals color times d, right? So we're going to set it to plus equals, because we want to add this into it. We don't want to just explicitly set it. We want to add it to it, because that'll allow us to keep blending these together, right? So now we have this. So this is our first point here. So what we can do is we can just do first point like that, so we know that's what it is. And then down here we could say second point. It doesn't really matter how you type that because it's not being read by the code when you have it commented out like this. And so what I'm going to do is I'm going to copy and paste this whole block because we know that this can now work again. And we're going to, instead of just looking at the first point here, we're going to say 1 to get the second point. And so now if I control enter this, you can see that something has changed here. It hasn't changed drastically, but there certainly is a difference. I'm just going to slide down here so we can look at this. So now as these go bigger, we're going to see that we're actually going past the boundaries of that initial just Voronoi pattern into kind of starting to blend these colors together. It's not working perfectly because we're only looking at 2 points, right? So you might start to think, oh my gosh, like if we have 20 points, that's going to be crazy and we don't want to do that. So there is a better way and we're coming to that. But first, we're just going to finish our thought on this near points and arrays and things like that before we go on to this kind of what's the better way of doing this. This is just seeing exactly how the code is being operated. It's doing one thing, then it's doing it again just on another point. So you can think, oh, I think I can probably see how this is going to go. We need a way to be able to kind of loop over this, right? But we'll get there soon. All right, so more on near points. So what can be really helpful is, in the middle of your code, like to debug, to send kind of your intermediate results to a temporary attribute. That's really common. A lot of people do that. So we did this a little bit earlier, but let's just talk about it again here so we can kind of see how this would work with a function like near points. So what we can do here to see it down in this, down in our geometry spreadsheet, forgot the name of it. Let's just clean this up a little bit here. Actually, you know what? We could do this just in one spot right here. So right at this point, we now have points. So you can see here we have int points. We've called that up here. And we have points equals near points. And we're doing that right here, right? So what I'm going to do is I'm going to say because we want an integer array. So I brackets at a equals points, just like that. So now if I hit Control Enter, that is going to write the near points of the current point that we're iterating over in our wrangle to this attribute called a. And we can see as we go down here, these numbers are going to change, right? Not drastically because there's only 6 of them, right? And they're going to be kind of in groups, right? Because they're going to be around, this next point as its closest. But you can see that this is changing down here. And that's kind of how you might help yourself know what's going on with your code, right? So now we can see that, yeah, this seems like it's doing the right thing or whatever. Great. You could possibly, you could take that out then once you're starting to get through here, because you probably don't need this down the line, like down in your code, like down your tree, like after the output of this wrangle. So you could just delete this, or like Matt says here, you can quickly comment or uncomment a line with control /. So if I do control /, that's going to comment that line out, then control enter, and that's not going to have that attribute anymore. So we could use that as like, a test attribute. So you could give yourself a little thing like, hey, this is a test attribute here or something like that in your code somewhere that's commented out that if you wanted to bring in again, there you go. Now we have it. So it's kind of a quick way to comment and uncomment something like that by using control and /. Okay. So, near points takes another argument at the end of it, right? So you can tell it how many points to return. So it doesn't have to just arbitrarily return as many points as possible. You can kind of give it, you can limit it, right? So let's change this up a little bit. I don't think we'll be doing too much more here with this. So we'll get rid of this now. Now I think we're good, safe to do this. And we'll keep our int points here, just like that. Great. All right, clean this up a little. All right, so we're declaring int points. Then we get our points. And here we're going to use 12 units for our distance. And we're going to say just return 3. Just return 3 points for us. And that should be just fine. Now the color goes away because we're not setting a color. But let's visualize this, right? Let's kind of visualize how exactly this works. So if we have, if we did something like at p.y and set that equal to the length, len, that's going to tell us how many elements there are in that array. And this returns the length of it. So we'll just do points here. And so what we're going to do then to make this a little bit more interesting is instead of having 12 and 3 just hard-coded in there, we are going to put 2 channels in there, right? So we'll say ch, because we want this to be a float for the radius. So we'll call this radius. And that's already there, so that should be ready to go. And then instead of 3, we're going to do chi and say num points like that. Great. And let's hit enter here. Should be good. Yep. And let's just have it add in that num points. And so now you can see here that we're actually visualizing based on the number of points that it's putting into the array. It's actually pushing that up and stepping this based on that. So as we bring the radius down, we can see, okay, yep, it's growing past those 2. And then, okay, now it's starting to overlap into 2, then 3. And if we go further like this, we can have 4, 5, depending. Now, I don't think it can go past 6 because I think, yeah, we're only feeding in 6 points, right? So here we can kind of change, this is almost like you can kind of crop the top, you can kind of clip the top of that off by setting it only to have 3 points. It can only go maximum of 3 high. So 6 obviously is kind of the high end there. We can just keep going here and see that grow up and down basically, right? So this is a way to kind of visualize, like almost like terraform this grid based on how many points are getting put into that near point array. And if you see these little sliders here, you get those just by pulling them out onto your viewport. So you can actually click and drag this onto your viewport. So it'll make like a little slider like that. And if you hit enter, now you could actually do that over here and set the number of points right in the display. And if you want to get rid of that, you can right click on it and just hit display like that, and it'll go away. So, and you can turn it back on just like that too. So you could right click over here, turn them on and off. Cool. So that's kind of a neat little extra tidbit there. Not really Vex, but a cool little HUD thing. And all right, so let's keep moving on here. Let's look at doing something like waves again, like we've done in the past. So we're going to use the same normal setup that we had done before. Distance to the closest point as d, and then generate waves with the sign of d, and then add some controls to set the frequency, amplitude, stuff like that. And we're going to use a separate variable called w to do our calculations on. That's going to be kind of how we do all of our calculations, because we don't want to get rid of d. We want to keep that and then use that at the very end to multiply on use that to multiply and have like a fall off based on the distance, right? So so that's why we're going to split this up and do our like math on w. So all right, so we're going to get rid of this and do something a little more visually interesting. Great. All right, so we're going to do int of points, a point array, I should say, like that. And then we're just going to set an integer called point as well. We'll do a vector type called pos, and we'll do 2 floats, d and w, just like that. Great. All right, so then we're going to do points is equal to near points, just like that. And this is going to be set. We're going to pull in the second geometry to do that. So we're going to put in 1. We're going to look at the position of the current point that we're working on through our wrangle. Then we're going to use a radius and number of points. So first of all, I'm going to just real click here, delete all spare parameters. So let's do ch of the radius, like so. And then we're going to do the same thing, chi. We'll call this num. Like so. 2 brackets there to close it off, and we should be good. So let's just do that. Okay, great. All good. We'll make those 2 things there. 2 sliders, and we can do number of points set to 3. You can see here how the integer channel makes this like parameter that has these little notches here for how many are in it. I think it defaults to 10, but you can change that in your parameter interface if you wanted it to be a higher number. All right, so we've got the number of points here that we're looking around it, right? So we've got our near points that we're storing. So let's just pull out one of those points. We'll say PT is equal to the first. So we'll say points 0. So that's the first index of that array. Then we'll say pos equals, and we'll say get the point of that the position of that near point. So we'll look at the first or the second input, look at the position P, and then use PT, which is our current near point, right, that we've pulled out of that array. Then from there, we're going to set D equals to the distance between .P and pos. Pretty standard stuff that we're doing so far. Nothing too crazy. I don't like to have that space in there. It's fine, but just looks sloppy. So I'm going to make sure that's right. All right. Then we're going to start doing some of that math on W, right? So we're going to say W is equal to the distance times a channel called frequency. Actually, we'll just call it frequency like that. Better than that than typing the whole thing out. So let's do that. So now we have a frequency. We'll just set that to 1 right now. Probably need to be higher, maybe like 5. So what that's doing is just scaling the distance so that the sine waves will be either higher or lower frequency depending on how we set that. All right. So let's also set W, and we'll subtract it by time, and then multiply time by channel called speed, like this. And that's basically just going to be making it so that the waves kind of progress over time, and we're using our speed to kind of tweak how fast the time is progressing, right? So, just basically multiplying it by a float. So we've got that, and we're going to set the speed to something like, 2. Just guessing at some attributes or some values here. All right, so now on W, let's run our sine function because we have the frequency and speed set, right? So now we can actually run our sine function on that. So we'll do W equals and say the sine of W. Okay, so now we have our sine waves. And then from there, since we have our sine waves, we can now change the amplitude of them, right? We couldn't change the amplitude prior to doing that because its sine function always returns 0 and 1. So let's just do W times equals, and we'll say ch amp for amplitude, like so. And the amplitude, we'll just set that to be 1 for right now. Don't need to go too crazy with that. And then the last thing we're going to do is what we had done before, that kind of inversion of our distance, right? So we're going to take W and multiply that by the fit value of D. So this is where we're bringing D back, right? Before we had used it and calculated it, and we've been working on W so far. So now we're pulling D back in. This is why we couldn't overwrite that. So we're saying fit of D. So we're taking that from 0 to the channel radius. So that's the same as before. And then we can do, we're going to take the low and set it to 1, and the high and set that to 0. So we're inverting it, right? Put a semicolon there. And then we're going to set our p.y plus equals W. So whatever that W value is, that has now been scaled by that, the radius, which is going to kind of feather it out at the end, we're adding that into our Y position for this grid. So let's hit enter, and there we go. We're starting to get something going on here. So you can see that as I tweak the radius, that's going to grow around it, right? Just like it did with our color, but this is the distortion. So let's bring the amplitude down a little bit. Doesn't need to be that high. So let's do something like that. And if we hit play, we'll see that this is going to be a kind of evolving, look now. We have each of these points are the center of this like sine wave that's going here. We can up the speed of it. So we can kind of go a little more crazy with that if we'd like to. we could turn the frequency down and we're going to have more smooth waves going on here, right? Or we could do something like this and bring the radius down or up. Now you can start to see that same non-overlapping issue here, right? Where we're not actually getting these waves to kind of feed into each other. It's the same thing we had before. However, we need something a little bit better for that, right? We need to kind of go past what we have here. So another thing Matt was mentioning was that if we have the frequency set too high, something like this, we're going to get really kind of ugly results here. This is 6. Even if we say we go up to like, I don't know, something like this, 7 or whatever, we get these really ugly kind of artifacting things because we don't have enough polygons to really work with that kind of, points and polys to be able to deform properly there. So we can up this a little bit here to be able to get some better results here. So we can, I don't know if he actually explicitly says how far he goes with it, but I'm just going to go up a little bit higher here. I don't know, maybe 150. I don't know if it really is going to make that big of a difference, but something like that, right? And so now if we look at this, kind of click off of that original thing there, now you can see that this is a much smoother result, right? So we're getting a much nicer, much smoother kind of resulting geometry here because we give it more divisions to be able to make these waves based on that. So if you have a really high frequency, you need to have higher number of divisions in order to kind of make that work. So great. So that's looking pretty cool, but we need to see we want to see what happens if we go into the next, part of this, right? We want to add those next points. So what Matt says here is that you can kind of visualize what's going to happen here by setting our code slightly differently here. So I'm going to take the amplitude maybe down a little bit, something like this, maybe 0.1, right? And so now instead of looking at this line right here, where we're looking at the first point in the array, let's look at the second point in the array and see what that does. So now what this is doing is this is looking up that second kind of second point position and using that to calculate all of our deformation off of. And that is kind of the fall off that we need to add in to be able to start to blend these together. So this is kind of the next step of that. And if we lower the radius here, we'll see something like that, right? Where we're getting this extra little bit of fall off here, right? So if you go really far, it's going to be just kind of to the edges of these individual cells. So let's just bring this back a little bit here, and we can see some of that fall off that we're kind of looking for, that we want to add into there. Because when we're looking at 0.0 again, we can see it like this, and we get these hard edges. But when we look at this 1 like this, we're going to get these values that we can blend all of those together. So just like we did before, let's take this block and duplicate it. So we'll set this back to 0 like this. We'll copy and paste this. And what you need to be careful of is that you're doing this p.y plus equals and not just equals, right? So that is kind of the important thing there. So let's do this set to 1. We'll hit enter. And now we can see that these ripples are actually going past those boundaries, right? They are not stopping at the individual boundary lines, right? We do have a little bit of weirdness going on here, which you can see slightly in Matt's example. I believe if we look down at the bottom here, he has that going on over here. It just has to do with the kind of the boundaries of that next point cell kind of, and it's some hard edges for that basically that we're seeing. So if we go far enough, we won't see that anymore. But we can see now, okay, we're getting some blending there. And you can imagine that if you keep going with this, we're going to get some really nice results. So that is the end of day 12. We're going to continue this kind of thought process as we go further. This isn't going to be the end of this talking about this exact example. So if you're like, wait a second, I want to see kind of the full result of it, that'll be in the next day. But let's talk about some exercises. If you guys have any questions, please feel free to put them in the chat, comment below the video. However, if you're watching after the fact, obviously comments will be available underneath the video. But yeah, if you have any questions, I'd love to talk about it, love to make them clear. But let's go through the exercises while maybe you're typing those questions up, and we can circle back to those afterwards. So first exercise is to make this extend beyond to more scatter points by manually copying and pasting. So kind of what we just did there. Manually copy and paste that more times in order to make this a smoother and smoother result that's kind of incorporating past the boundaries of those near points into each of those different cells so that you have a nice smooth result. So make the waves include and mix color. So instead of just doing it with the position, do it with color as well. Pull in the color and blend those together as well. And could you do something where you have different speeds and amplitudes for each wave? So the hint is you'll need to add a random amount to W somewhere, and you have to drive that based on whatever the point number is that you're reading, right? So that's your little, offset. You could do some sort of interesting offsets for each wave kind of center, so that they're not all uniformly going up and down. So yeah, you could certainly do that and do different speeds, amplitudes, time offsets, things like that. So there's a lot of ways you could extend this. All right, so there we are, Joy of Vex, day 12, and we'll be getting into 13 here in just 1 second. All right, let's do day 13. And this is where we start to get into some really exciting things, I think. I'm just going to slide these over like this. And we'll at least start from here if we need to and kind of go from there, right? All right, day 13. Start to talk about something I think is really exciting. For each loops, which I guess shows how big of a nerd I am, because for each loops are apparently exciting to me. But this is really cool, and this is, I think, where some of the beauty of the parallel processing in Vex really gets going. So obviously copying and pasting chunks of code is lame, and that's not what we want to do. We want to do this a little bit easier and be able to write our code once and not have to copy and paste it, because obviously if you were copy and pasting that and you needed to change something, you have to change it in each instance. Better to change it once and know what it's looping over. So that's where for each comes into play here. So this is how a for each looks. You use a for each function here at the beginning. Then you say, then you define an element that it's going to set on each loop that it goes through that for each, right? And that's like a temporary variable, right? And then you have the array that you're going to loop over. So for each of, for each of the elements of the array, return that element and do something to it. And we do the something in here, right? In between these curly braces, right? So we refer to that temp name in there, and will be able to pull that out of the array anytime we need it. So in this case, it'll be able to pull out each of those near points as we loop through them. And we don't, when here we say point equals to points 1, we don't need to define that anymore. It's going to loop through those within our code. So, so that's all well and good. I am going to, yeah, we'll get rid of this. We'll start fresh. Let's just start fresh. Why not? We'll also delete our spare parameters because we're going to be doing some different things here. We're going to first be looking at color. So let's look at a color example here. So we're going to do vector attributes, pause and call. And we're going to make a integer array called points. But we're going to store some point indexes in there. We'll do int point. We're going to use that within our loop. And let's do a float d. And that's going to be our distance. All right, so let's set points equal to the near points. Just need the plural one. And we're going to set that, look at the first input here, because we're still using that scatter and color that we had before. So that's going to be coming in there. So it errored because I clicked on it, but that's okay. At P, and that's going to be the position we look at. And we're going to go search 40 units away from it, like so. Then we're going to initialize the color here. Oops, at CD equals 0, just like that. And then do a semicolon. Great. Let's just, oh, and I mistyped here. I said flowed, meant to say float. There we go. All right, so we've got our nice black grid that we can start with, our nice kind of starting point here. All right, so now we're going to write our for each loop. So we're going to say for each, and we're going to say point. That's going to be the element that we use each time. That's going to be an integer. We define that up at the top. So we're going to do point. And inside of a for each call like this, we use semicolons to separate the different kind of arguments within it. So point, and then we're going to loop over the array points. Okay, so this is kind of for each point in points if you're used to doing something in Python. So that's kind of the same nomenclature here, right? So we're going to do our curly braces, and I'm just going to go back up and tab in, and this is going to be what runs on each loop, each iteration of this. So again, we're going to say pause is equal to, and we're going to use our point function on the first input in order to get the position, and we're going to do that for the current near point of our array. So that's PT. Again, we're going to go down here and do call. Call equals the same thing, point of 1. Instead of P, we're going to do CD. So that's the attribute we're reading. And we're going to look at the current point again. Cool. So now for our distance, we're going to do D equals distance. And this is going to be the distance between the current point that we're looping over in the wrangle and the position of the near point that's in the for each loop within the wrangle. So we're looking at, if you're thinking about how this is working overall, we're going over, we're doing this on each point. We're running this code on each point in our grid. And then within that, we're doing this for each, looping through every point that comes up in the array. So it's kind of two nested loops that are happening there, right? The one is just kind of inherently happening within a wrangle. It goes over every point, but then this loop runs on each individual point. All right, so we're doing that there and getting our D attribute. So let's take D. We'll do the same thing we did before, which is fit that and invert it, right? Based on the radius. So we're going to say fit. That was weird. It's supposed to be like that. Fit D. And we're going to say 0 and the float channel called radius. That. We'll be flipping that to set the low to 1 and the high to 0. Meaning the further it is, it's going to go to 0 within that radius. And then at the end here, we're going to do a clamp just to make sure our values stay between 0 and 1. So we'll say D equals clamp that and D 0, 1. Just like so. And then we're going to say at CD, capitalize that C, say plus equals. So we're adding col times D to our color, just like that. So let's hit Control Enter, make sure we didn't get anything wrong here. And sure enough, we did get something wrong. And the something wrong we got was here. And this will come in later, but we can see that this syntax is happening here. And what it's saying is it was an unexpected identifier. It was expecting a semicolon. And where it was expecting the semicolon was right before it on this line. And there it is. Now we should be good. Great. We also need to have it add this parameter here. And now we can up our radius. This looks pretty similar to what we had before, but you'll see that as we go further, blending colors. The colors are blending. And so now there are no lines because it's using every individual point that's in its array. You could go up to as many points as you can imagine, and it's going to blend all of those colors together, right? And just even as an example, if we did 20, and we'll bring the radius down because it's obviously blending quite a bit. But you can see here now, all of these individual points, it's blending across all of those smoothly without any, edges that it's kind of creating. And this is, again, where some of the power of Vex comes in, because this is running super, super fast, doing all these calculations, running this multiple times on each point on our geometry. We have 22,000 points in our geometry because I didn't even lower the resolution of it, right? Like of this grid. So it's running this code a lot of times massively kind of in parallel over our geometry. So really exciting when you start to think of some of the things that can happen here. What did I do? Did I set my grid to 1 or something? Oh, that's weird. Center was off. I don't know why. There we go. Not that it matters that much, but okay, so let's set our scatter back to 6 just so we're not going too crazy here. So we'll go back to 6. Up our radius a little bit more, and there we go. Nice smooth colors, just like Matt shows here. So Matt says, just because it's late and I'm tired, we're going to use the usual wave to see how this works. So we're going to be doing kind of the same thing we did before with doing the position, the Y position, based on some of those things we had before. So all right, let's grab some of these things here. And this is going to look a little different than it did before. And we'll talk about that in a second, kind of maybe why it looks different. So, okay, so let's do the vector pos here. We only need that, int points, integer of point, float, and we're going to do A, D, F, and T, just like that. So again, we're going to be doing points is equal to near points, search within 40. Great. Don't need to change that. CD doesn't need to be there anymore. That's cool. That's freaking out because it's trying to set something that I didn't define yet, so that's okay. So let's get rid of this in here and we'll start rewriting this. All right, so actually, you know what? We can just keep that first one because that's the same. No reason to write that same code again. So we'll do D equals distance is the same thing actually too, but that's okay. We'll get some little bit of practice in here. So we're going to do the distance between P and pos, which if you remember from before, pos is the current position of the near point. Then we'll do D equals fit D0 and then the ch radius like so. And we're going to invert that, right? So 1 and 0. All right. So then here we're going to clamp it. D equals clamp D, comma 0, comma 1. So we're just clamping it between 0 and 1 in that case. So then now T, we're going to use this as kind of our time. So we're going to say at time times ch, and this one will be speed. Right? So now we're taking our time, this pseudo attribute time, multiplying it by our speed channel, so that we can have a slider to be able to work with the speed of our waves. So then we're going to do T plus equals random based on PT. It's going to give us a random number based on our current point that we're looping over. Might think back to day 12 there, little hint. A, we're going to use set A times the distance and the amplitude here. So we're going to say ch amp. So now we're multiplying the distance by a float called amp. And that is going to adjust the scale of this distance so that that's going to that's interesting. It's multiplying by D. So I guess that's taking the distance and having, yeah, that's what it's doing. So it's using the distance to kind of make a fall off for the amplitude so that it doesn't just continue off forever, I guess. So it's kind of making, it's multiplying the distance by the amplitude so that the amplitude decreases over time. So that's cool. And then F is the frequency. So this is going to be D times ch frequency like that. And then the final step is going to be at p.y. So we're setting the y component of position. And and we're going to do plus equals because we want this. This is going to have to kind of run multiple times. So we don't want to just set it to something each time. We want to add it in there because sometimes a sine function is going to be positive. Sometimes it's going to be negative. So as we add positives and negatives together, it's going to kind of blend those all together. And so here we're going to do plus equals the sine of t plus f, right? So that's time plus the frequency. And then we're going to multiply it times the amplitude. So this is a little bit different than the way we had done it before, but maybe a little cleaner for doing it within a for each loop like this. And let's hit enter and see what happens here. So now, we also need to do all of our channels down here. So speed, I don't know, we set it to 2. Amplitude, we'll do maybe 0.1 again. Frequency, gosh, I don't know, 10. We'll see kind of how this looks. There we go. We can kind of play around with that. There's our amplitude, and then our frequency, we can up that as well. And then we can play this. And if I up the speed a little bit here, see that animating and having some smooth blending between these positions here. And you can bring it back, right? So we can bring our position back. Those will just start to slowly blend into each other. And we'll get nice smooth blending kind of, irregardless of how far we go with that radius. Just get some really interesting results here, I think. We can lower these down a little bit so they're maybe not as high. We could say maybe 0.2, something like that. We can up the frequency so we've got maybe some smaller waves that are all kind of crashing into each other, something like that. Right now we've got all these things that are kind of blending together as they, are further apart. And it doesn't matter how many points we put into this, right? We could add more and more points and it's going to just loop that over more and more points. So just something to keep in mind that this is happening, multiple times for each point, and it's doing that incredibly quickly. It's able to play this back real time. As you can see here, we're running at 24 just fine. So again, just another thing to note is that depending on how big your grid is, right? Say, like he says here, say 50 by 50 with 100 by 100 divisions. So here, if we took size, set it to 50 by 50 with 100 by 100. So that's going to be quite a bit bigger. That you'll have to set, you'll have to set the radius to 8, the frequency to 10, he's saying here. So let's just do that. Radius to 8, frequency to 10, something like that. And maybe we even need to go quite a bit bigger and really up the amplitude as well. So that would be visible there, right? But if you change this to say something like the regular 10 by 10 grid, that's not really going to work here, right? That's just way overkill and doesn't really make any sense. And the amplitude is way too big because you're moving it up by 1.5 meters. So that's, again, not going to do too well. So you got to kind of play around with how this works. The frequency needs to be higher for a smaller one. The radius a bit smaller, and the amplitude lower, obviously, for something that's a little bit smaller like this. So just something to keep in mind there. Some things that you have to kind of tweak around. All right, so we have our for loops here. So let's talk about just a regular for loop. This is a little different, and we'll talk about how this differs and maybe where that's beneficial, for working with, right? So let's first talk about how this is structured, right? So the syntax is a little bit harder for writing these. So for a for loop, you give it a starting value, you do some sort of test on it, and then you increment the value. So let's first look at this and kind of just do a really silly contrived thing just to kind of get an idea for how this works. So we'll do int I. Let me get rid of our spare parameters here because I don't think we're going to need those just yet. All right, so we got int I that we're creating. And what we're going to say is for I equals, oops, sorry, that's 1. I equals 1, like this. Then do a semicolon. Now we're going to do the test, which is while I is less than 11, and we'll say I plus plus. So we're going to increment I each time. We'll say A is equal to I. And A is 10. Because what it's doing here is first we're setting I equal to 1. We're checking if I is less than 11, which 1 is less than 11. And then we're incrementing I by 1. I plus plus, kind of a shorthand for it, right? So then we're setting A equals to 1. Or A equals to I, sorry. Then we're doing this whole thing again. So now we're going to come back up to the top because we still had that we have to do that check again to see if we're done with the for loop or if we need to keep going. So now we're going to do, we already set this to the beginning, so it doesn't set every time. So we're going to check this time and see if I is less than 11. So it was 1, now it's 2. Is that less than 11? Yes. Add to it, which is going to make it 3, and then set A equals to I. Then it's going to come back up, check again. So it does that over and over and over. And once we get to 11, it says 11 is not less than 11, so that's false. And we don't need to add anything to I. And on the last step, A was set equal to 10, right? Because we incremented it before, the very last step. So in that case, I coming in was 9. We check if I is coming in, I was equal to 10. We check if 10 is less than 11, which it is. Then we do I plus plus and set A equal to 10. And then when it comes back up to the top and does that check the next time, it fails. So A is equal to 10 is the last thing that was run, and it exits that for loop and goes on to the rest of it. So kind of you want to set it to, it'll set to the last value kind of in this case, before it exits that loop. So it's a silly way to do it, but it shows kind of how it works. So we don't have the option to run it over an array, right? But we can figure out how long we want it to do based on how we write that function, right? So you can check the size of an array that's coming into it and use that, use a function called len, to check the length of that array. And so each time you go through your loop, you can increment that I, step it up by 1 each time. If you started at 0 and you compare to see if the number is less than the size of the array, when it gets to the last number in the array and does all of its stuff and tries to go back through it again, it's going to fail and then it'll exit that loop. So that is the way that you can kind of have similar functionality to what you were doing previously with for each, but using just a for loop. It takes a little bit more setting up to do, but it certainly is a very, similar concept, right? All right, so let's just go back here and start writing this out. So we'll do the vector, pause, and call for color. So we're going to be doing the color example again. So we'll do int point, and this is going to be an array. Then we're going to do int I and pt, because we're going to use I in our for loop. So we're going to declare it up here. And then we'll also do a float d. So we'll do the points equals near points, like that. And we're going to do 1, look at the point position, and look within 40 units of that. Again, we're going to initialize cd. And now we're going to do our for loop here. So we're going to do for. First, we're going to say I is equal to 0. So that's kind of our starting point for our array. We want to start at index 0. So we're going to put a semicolon there. Then we're going to say when I is less than the length of the array points, that's when we want this to go. So once it gets past the length, the number of elements in that array, it's going to fail. And we want to increment I each loop. So we'll do it like that. All right, cool. So this is going to be the same kind of stuff that we've done before. So we're going to say PT is equal to points and use the I in there to say what index of points we want to read out. So this is kind of like how we had done it previously when we were copy and pasting that, but now we're using the I variable to be able to set which element of the points array we're getting each time. So then we're going to get the position of that near point. So we're going to do point 1 and get the position and use the current near point for that. Same thing with the color. We're going to get the point 1 and we're going to do CD point like that. So now we've got the CD stored in col, and we're going to do the distance again. So we'll do D equals distance of the current position and the near point position. I hit enter twice there. So then we'll do D equals, so we're going to do that fit again. So we'll do fit of D 0 CH radius. Then invert it like that. Do the clamp again. Clamping it between 0 and 1, like so. And then we're going to do at CD plus equals, because we want it to add each time and not just set it once. We want to add it kind of as we go through this loop. CD plus equals col times D, which is going to give us that fall off value as well, based on the radius. Let's hit enter and add in that parameter. Sure enough, we're getting those colors and they're all blending nicely. So this is that the same thing we had done before, but just using a for loop and just slightly changing the way that we write our code based on the fact that we're using I for each of our elements and not something like PT. We're not getting PT out of the array. We're not really we're not actually talking about the array in this case. That's not what we're iterating over. We're just iterating until we've done that, an equal number of times as the length of our array, the number of elements in our array. And again, there's a thing you snuck in there, I++. We kind of talked about that. It's the same as I equals I plus 1 or I plus equals 1. So it's just a shorthand for that. And so there we go, for loops. Hopefully that makes good sense to you. It is definitely a bit of a complex idea. So if you're struggling with that or struggling to understand how that works, please put a message in chat and we'll talk through that a little bit. But this is, I think, where really the power of Vex starts to come into its own, and you can really see how amazing this is, because you get this nice kind of clean way to see what's happening as you're looping over information within all of your geometry in your scene. You can do some amazing things with this. You can also do for loops and for each loops and things like that in VOPs as well. It's just a lot harder, I feel like, to understand when you're looking at nodes versus actually looking at the code here. I feel like the code in a lot of cases is way easier to look through and see what's happening than trying to follow a trail of nodes to see how things are looping and all that kind of stuff. So just something to keep in mind, this stuff is possible in VOPs as well, but I think a lot of times it's easier to do it in Vex. And if I'm doing for loops and things like that, I'll pretty much always do it in Vex. So all right, let's talk through the exercises as you guys kind of maybe think of any questions or thoughts you might have. So first exercise is make ripples that are red at their peaks and green at the lowest points. Which is better, for each or for? I don't think that I wouldn't say that there's a better one, right? I think they each have, kind of their own uses. Pick one. All right. If you got a gun to my head to say pick one, I would say for each. I like the cleanliness of being able to take an array and pull out the elements each loop. I feel like that's to me is a little cleaner and a stronger way to do it. especially because like in this for loop here, you're actually calling, kind of doing what a for each loop does within it, right? So from that standpoint, I would say a for each is, in my mind, I use that more often than a for loop. But there certainly are times where you need to use a for loop because maybe you don't have an array or something like that. So anyways, I'll say for each is better, but not to babble on forever, but that correct answer. Oh my gosh. Yikes. Matt, you're so violent. All right. So let's talk through some more of these examples. And if anybody else has got questions in the chat, happy to answer them. All right. So make each ripple setup have the wave frequency be determined by data coming from the scatter points. So either the frequency is set by the point number or maybe the X position of the point. Use something like that you're pulling off of the points to set something on the frequency. And then the last one is kind of an interesting thing because it says, Matt says, I initially had an exercise, quote, make the color example do a color blended multiply mode rather than additive. So right now we're adding the color together, but instead he's saying multiply it, do it like a multiply operator would be in Photoshop. But it's not easy to get right. He included the finished result below, and the exercise is kind of pull it apart and try to understand why it works the way it does. So this is the example that he's talking about here, and you have white, and we're doing a multiply, doing some interesting stuff there. So try to pull that apart and see what you can figure out there. And if you're running into trouble, you can always hop on our Discord server and drop it in there and be like, I don't understand why this is working the way it does. Or why it's doing this or whatever. So try it out, see what you can do. And you can always, make some comments in there, or heck, any other Discord server that exists. Maybe the kind of public think procedurally one, or Matt has a Discord server as well that you can use if you are a patron of him. Patreon? My brain is like, I didn't do work today, so my brain's a little fuzzy. Patreon is the name of it, but you become a patron. Weird. Anyways, I don't know, a patron of my Patreon. Yeah, that's weird. I'm like reading that, and then now my brain just totally freaked out as to what the actual name of it is. But anyways, if you do that, you can get on his Discord. Super helpful there. You'll get quick, easy access to Matt's brain and lots of other great people on there as well. So give that a thought too. If you'd like to throw him a few dollars a month, I think he would definitely appreciate that. And so that is day 13 of the Joy of Vex. Guys, we're cruising here. We're going right along. Let's get into day 14 now. As long as no one else has any other questions or thoughts about this, we can move right on ahead. All right, day 14. Let's do it. So now I think we get into something pretty interesting here, which is creating geometry. So I'm just going to do this here and slide it on over. Let's reset this, control middle click that, and then delete our spare parameters. There we go. So we've really just been manipulating geometry, but Vex is also able to create geometry as well, which can be super, super helpful in a ton of different cases. I'm just going to reduce the size of this a little bit, since we will use it like that. And I'm going to cut that, and I think I'm just going to delete these as well. We don't really need those right now. Great. All right, so let's start playing around a little bit with how some of these geometry creation functions work. So the first one we are going to talk about is the add point function. So here we have the way that this is created here. So it's always running on the first geometry, or 0, right? We've been using 1 like in our point function, and that refers to the second input. Add point always uses the first input. There's a note in the help documentation that this could eventually become, there could be an addition to this in the future in order to make it add to other geometries coming in. I'm not sure how that would exactly work, and that doesn't totally make sense to me, but maybe that's like a long-term goal of someone, or maybe that's just been in there for like 20 years and nobody's going to do it. I don't know. But for now, we'll just say it always works on 0, and we'll go from there. So let's just write this down and we'll see how this works. So we'll say int pt equals add point, and we're going to do that on geometry 0. And we're going to make this point at a certain position in space. So we're going to create it at 0, 3, 0. We'll do that in curly brackets, close that bracket, and control enter. And now we have one point that is at 0, 3, 0 in space over top of this grid. So it has added that point and called it. And what it does here at the beginning here is it actually will store this new point position number, the index of that point position, in this attribute PT. And it'll do that for every point that it creates, right? Every time it loops through, it's going to change whatever the point position it's making. And as I say that, now you might be thinking, well, hold on a second. That means that there's a lot of points up there. And that's true. If we turn on our point numbering, we can see that this is just a jumbled mess. Maybe you can see it, maybe you can't, but this is just a jumbled mess. You have to take my word, because what it's actually doing is adding a point for each point, right? So we have 100 points on this grid here. Like if we select this, we have 100 points there. We come down here, we now have 200 points, and 100 of them are right here. So it's kind of a weird way of doing that, right? So you could do some SOPs based stuff, right? You could use a fuse to like collapse it down to a single point. But let's just do it a little bit cleaner in our function, so we can do an if statement here. So let's do this a little bit differently. Let's put an if in here. So we'll do if at ptnum equals 0. So only run this on the first point number. We'll do that. And then, oops, sorry, let's move that out of the way. And there we go. So now we have this. We're saying if point number is equal to 0, add a point, and should just be 1. And sure enough, there it is. Point number 100 is up at the top here, and we have 101 points. So that's good. Now we're doing something that's a little bit more appropriate for maybe just adding a point in space and not having to do any weird fusing after the fact. You could also do it this way as well. So we could say just run it over the 0 point like this. So this function will only run when it has this point number, right? So we could do it, 5 if we wanted to. It's still only going to make 1 point because it's running on the 5th point that's on the incoming geometry. Okay, but back to the parallelism idea of Vex. So we have an add point, but instead of just putting it arbitrarily in space, let's do this. Let's add the current point position to our arbitrary, vector that we have here, and take this group off because we don't want to do that. And now we can see that we have a point in space that's 3 units above the grid for every single one of the points that are in it. So now we have 200 points. They're all sitting at their own distinct 3-unit above their corresponding point on the grid. So this is kind of a neat thing to kind of understand. And the reason that we can do this without setting that int pt is because we're not doing anything with that point. It can be run just by itself without having to set, without having to set an attribute, or a variable to the result of that. So we don't have to say like, oh, this is point number 100. We're not doing anything with it. It doesn't matter. You can write an add point function just like this without having to set it equal to anything to start. So just something to keep in mind. So, so we have that. So let's now talk about creating a point that maybe sits 4 units away in the direction of the normal. So here we're going to do P. We're going to add the normal, right? And then multiply that by 4. And in this case, since the normal is just up, it's just putting a point 4 units away from the normal. I'm going to turn these point numbers off. It doesn't really matter for us too much. So that's all well and good, right? Makes some sense. We're doing it for each normal, but it's just a grid, so we're still just going up 4 units in the calculated normal direction. All right, so let's take this idea and kind of combine it with what we learned from for loops. And so let's do this. This is a case where a for loop is pretty helpful. So we want to add, what we're going to do is we're going to run this 10 times and add a new point each time. And each of those points will be 0.1 units further away from the original position. So here we go. We're going to write a for loop for this. So let's do for, and we'll say int I equals 0. So we can actually declare that variable right there. We don't have to declare it earlier. So I equals 0, while I is less than 10. And we're going to increment I 1 each time like that. Let's put in our brackets, tab that over, and just for cleanliness, we'll do it like that. And okay, so now we have to tweak this a little bit, right? Because we're not just going to multiply it by 4. We're going to take that and multiply it by I, which is the current iteration number, basically, times 0.1. Just like that. I think that should be good. Sure enough, there we go. So now we have points that are each 1/10 of a unit further than the previous point was away. So we're basically making 10 points here that are each 0.1 further away from the original point position. So kind of an interesting thing, right? So the loop is like a counter, right? It's counting each time. So we start at 0 and we count up to 10. Basically, we want to go from 0 right here, starting at 0 up to 10. And we're iterating it each time. And then that's like a little counter, variable for us that we can use, right? So we can it just keeps going through that and it's all good, right? So, okay, so this is points, right? We have points here. But what if we wanted to do something like lines? And, Matt mentions here that he's assuming that you've read this page, his points, verts, and prims. I'm going to copy that into the chat here in case anybody hasn't. There it is. So this is basically explaining, what the difference is between, each of these different, geometry types and attributes and things like that. But so what you should know probably by now is that, in order to make a polygon, you have to have a bunch of points that are linked together as vertices, right? So a primitive has multiple vertices that are defined by points. So so it used to be that where you'd have to have points and then make a prim and then link them together using vertices, like by saying which vertice they are. But now there's some convenience functions and we can do that a little bit more cleanly with the function add prim. So here we're going to start talking about that and how kind of that works. It's the same idea where we're running it over geometry 0, first input. And the type of primitive that we're going to make is going to be determined by a string, which usually is polyline. There's other ones that you can use, but polyline is just, a connected line that isn't like closed or whatever. So, and then you give it a comma separated list of point IDs. So, let's look at that first example that we did before, and we're going to, instead of just having a point, we're going to make a polyline between those 2 points. So let's go back and rewrite this here. So we'll do int pt, and that's going to be equal to add point. So we're going to be getting the point number from this, right, and setting it to the int pt. And this is going to be running over the first geometry, and we're going to be doing that at 0, 3, 0 like this. And semicolon. And then we're going to do an add prim. We're going to be doing that. We don't need to we don't need the prim number for anything. So we're just going to leave that. It's going to be 0 anyways, because we're only making 1. So we're going to add prim 0. And then the type is going to be polyline like that. We're going to do that based on the current PT num, and then so we're going to connect the current point that we're working on, and we're connecting it next to the int PT that we created, that added point up at the top. So we're going to be doing that, right? So we're going to be adding those two together with a line. And when we do this, we get this kind of interesting looking thing here, right? So in this case, it creates a point at 030 and connects a polyline. Now the problem is that this does the same crazy thing at the top here where you get a whole bunch of points. So you'd need to do something like fuse, or just have it each time refer back to that, and not add a point each and every time. So there's some ways you'd have to go around that. Fusing it would be a fine probably solve in this case, because it's probably a little quicker than writing the code out for it. But so instead of this, we could just make a polyline along the normal, right? So let's still do this in PT. We're going to add the point to 0, but instead let's do it using the current point position and adding in the normal. And then down here, we don't really need to change anything, because we're doing the exact same thing where we're taking the current point number and the created point number and making a primitive between them. So let's just hit Control Enter, and now you can see that we have a whole bunch of lines here, a whole bunch of polylines. So it's kind of interesting, right? We're getting somewhere here and making some interesting, like you can imagine how this could be used for things like grass and hairs and things like that. I mean, there's maybe better ways of doing that, but it's something that you could do with this kind of a method here. And so, all right, so we're taking these and making them along the normal, right? But what we could do too is move that top point with some noise in our vex function. So let's change the way we're doing this a little bit here. So let's first make a vector called pos, and we're going to set this equal to the normal, plus noise of the current position plus the pseudo attribute time. So that's going to kind of give us time varying noise based on the position. And then we're going to multiply that by a vector, 1, 0.1, 1. And the reason for that vector that we're multiplying it by is so that it doesn't change in its y position basically at all. And it's not like scaling these lines all over the place, and it'll just make them look like they're waving a little bit. Cool. So that's going to be the position that we want our point to be at, right? Because it's going to be in the normal direction, and it's going to be based on, it's going to move it based on the current position and time, right? And then scale it a little bit based on that last vector. So here now we're going to make a point at that position. So it's going to be at 0. Instead of doing p and at n, we're just going to say plus pos, right? Because we already set that position into that pos vector. And then the same last thing just will stay exactly the same. So now here we have 0 polyline, and just we're putting a line between the current point number and this new added point. And if we hit play, we'll see that we get some waving kind of weird little lines, just like that. So this should work kind of depending really on any, oops, didn't mean to do that, on any geometry you feed into it. So here's the sphere, right? So there's some lines based on the sphere, right? Doing some weird stuff. Maybe the pig head, there we go. And, you could even do it over Tommy, right? Maybe it gets a little crazier there because you can see we're doing this over more and more points, and we're trying to do this based on time. So it has a little bit more to calculate there. But yeah, you can do this based on, any of these different geometries coming in. It doesn't matter because we're doing it based on n. So yeah, that's looking pretty good. So let's do something maybe even a little bit more intensive here. So let's, instead of just doing it with one point, let's do multiple points along the normal, and each moved by slightly different noise. So it's more like, even more like wispy, instead of just Yeah, that's a great question. So the question is, how come this knows the n without that being on the points before you go into the wrangle? Yeah, that's a great question. I don't believe it'll change it at all, but let me just make sure that I shouldn't have been having this here. Yep. So the normal is just calculated kind of implicitly by Houdini, right? Because there is a normal on the, like, if you do something like this and just look at the grid without, oh, stop it from playing, there's kind of this implicit normal here, right? And so it's using that assumed normal to drive the normal that happens here, right? So that is why it's happening the way it is. There'd be no difference from it, right? If I set the normal ahead of time, which you can explicitly do that, right? Or sorry, not point, normal. So just like I did here, if I made sure this is set to points, yeah, it's going to set a point normal here. Now we have this blue normal instead of a vertex normal, and that's going to be the exact same thing, right? And in fact, here the normal attribute, whether this is here or not, is being set. And so when I'm calculating this right here, it's actually setting that normal at that point as well. So so whether it's set or not, it already kind of implicitly knows it. So that's why it works here. If you had actually, you know what though? Now that I'm thinking of that, it might not implicitly know this one. So let me just check, because I was thinking that looked a little weird. So let me try this. Normal. Interesting. So that slightly changes it. Not a ton, but it is calculating that normal a little differently based on what method you're using here. So that's kind of interesting. So it probably is best to set that normal ahead of time so that you know that you're getting the normals that you want for it to get, displaced along and stuff like that. But it can calculate that based on kind of implicit normals that exist on the vertices and stuff like that. So yes, that's how it works without having that set ahead of time. But we can just set it ahead of time too. Either way is fine. So we'll just leave it like that. But good question. Thank you for asking that. All right, so let's go into this a bit more wavy kind of noise thing here. And we're going to clear this out. I'm going to turn these off like that. And let's declare some variables here. So we're going to say vector offset and pause. Then we'll do integer PR, PT. And then we'll do a float. Oops. Step size. I should probably make that a little bigger. Sorry, that's been a little small. Hopefully you can still read that in the other lessons, or the other days that we've done so far today. All right, so let's first set. We're going to actually take this primitive number, right, that we're adding, right? So each time that this goes over the point, like for each point on here, it's going to be making a new primitive. So we're going to store that primitive number in this PR integer attribute PR. Sorry, my brain is off today. Integer variable PR. I'm just like totally mixing myself up there. So we're going to store that. We're going to create this variable here and then store this prim that we're adding. So we're doing add prim 0, and it's going to be a polyline like this. So our step size is going to be equal to 0.5. And now we're going to write a for loop. So for int I equals 0. And we're going to do this while I is less than 6. And each time we're going to iterate, we're going to increment I. All right, so this is what we're going to do each time in our for loop now. So we're going to set the offset equal to curl noise. So we're using the curl noise function. And we're going to do the curl noise over the current position minus the time pseudo attribute plus I. So that's doing an offset based on the iteration of this for loop that we're going through, right? And then we're multiplying that noise times 0.2. So that's going to be the scale that we give to that noise. So in our position, pos is equal to at p, and we're going to do adding at n, scaling it by the current iteration through this for loop, and scale it by step size plus the offset. And then PT is we're going to set that to the point that we're adding. All right, so we're going to do add point here and do 0 and pause. So that's going to set it in that position. So it's going to add a point in the position of the current point plus n times the offset set by the curl noise function plus the step size. So yeah, so there's quite a few things in there that are kind of helping to randomize this, using step size and offset, the current loop through the for each, and then the base is just that it's going to be p plus the n. So it's taking that position and adding n to it. So, great. So that will add a point in each of those, but we don't have that point added to the primitive yet. So what we're going to do is we're going to use the add vertex function. We're going to do that on the 0 geometry. We're going to do that on the PR primitive and add the point that we just made. Right here, you can see we set this add point to PT. And so we're going to add that point that we just made in that for loop. So now it's going to make 6 points, right? That's going to come up from this original point up in the y-axis, or the axis of the normal, based on the step size and offset and things like that we're calculating here. So the step size is how far, the offset is the noise that we calculated. So that should be good. So let's see what happens there. And sure enough, got some wavy, kind of crazy looking grass here. It's kind of going all over the place. So we kind of talked through this a bit, but let's just look at that too. So let's just look at this here. So here's our furry pig, and in fact, I'm going to scale this up a little bit so that it's a bit more appropriately sized here, something like that. If we change the step size as well, that would make him go less away from it, but there we go. So you can see that we've got this wavy thing that's kind of doing all sorts of weird stuff. And the question here that Matt asks is, why are we doing it this way, right? This is the older method for creating primitives that we mentioned before, where you make an empty primitive, make some points, and then attach those to vertices along that primitive. So the add vertex takes a primitive ID and a point ID. So we take this point ID and this primitive ID, and then whatever order you add them, that's the order that they go in your primitive. So as you're making those vertices, that's the order that they go in your primitive. So just a different way of going about creating primitives. And this is a little bit more, I would say this is probably a more useful way of doing this in the case of something like a for loop here, because you can add that vertex each time you go through the loop. You could also store them in like an array, I guess, or do something like that, and then put them all into that kind of idea where we had add prim and then had the points that we were adding after it. But once you get into, 20 of those or something, it's just going to get unwieldy, long, and ridiculous. So doing it this way is a lot better for something that's you want to do with kind of a varying number of points. Like if you could, in this case, you could have it do, we could change this to 8, And it should just, oops, sorry, should just add some more onto the end of it here, I think. Yeah, there we go. So there's 6, there's 8. I mean, you could do 20, right? And so this is a much more flexible way of doing it, basically. So there we go. There's a for loop, making some geometry using add prim, add point, and add vertex all together. So I would say that add prim is most useful when you're doing maybe 2 or 3 points or something like that. But once you get past that, I think it starts to become a bit unwieldy. So just, just something to think about. All right. So other primitive types. This is kind of an interesting thing to take a look at. I have the add prim help card here. We'll copy that over. There we go. I dropped it in chat for you. If we scroll down a little bit here, we can see the different types. So poly would be a closed polygon. Polyline would be an open polygon. We also have tetrahedrons, hexahedrons. Then there's also some primitives that you can define, like sphere, circle, tube, metaball, meta squad. I don't know what that is. I don't understand what that is, but I've never used that before. But you could even define alembic references, packed disk references, all sorts of things like that. So these are all the options that you can do instead of just polyline here. And so just as maybe like a simple example, what we could do is let's just do something maybe really basic here, just to kind of get an idea for how that might look. So let's take this, and really all we need is, we don't actually need any of this down here. Don't need step size. So I'm just going to explicitly like say what position we want to put this at, right? So we'll say, let's do the 0, 3, 0 again. Actually, I'd written this down. Sorry. Right. So this is actually what we want to do. Sorry, I'm doing this the wrong way. My bad. Because we want a point ID here. So we're going to say point, and here we're going to say point equals add point. Then we're going to say 0, and then we're going to give this the position, right? Because this point is going to hold the position, right? The polyline doesn't hold the position. Points do. So we'll say 0, 3, 0 here. And close that like that. Okay, great. So we have 1 point up there. All good so far. However, it is a polyline right now, which is a little weird. So it's not really drawing much of anything because there's like there's just a nothing singularity point there, right? So instead of this, let's do something maybe more interesting. So let's do a sphere. And there we go. We have a sphere primitive. Could also do something like a circle. And there we go. Now we have a circle primitive. So you can see that this is kind of an interesting way to do something like this. You could add, a bunch of primitives if you wanted to that way to kind of visualize something, or, whatever. There's different, I'm sure there's a number of different uses for something like this, but just something to keep in mind that this add prim isn't just for drawing lines or filled polygons. You can do primitives like this as well, where you can do sphere, circle, tube, things like that. So just something to keep in mind as you're working with that. All right, so removing geometry. So we've added geometry, but how do we remove it? And it's pretty easy. You use the remove point function. So here we can take this and we can say remove point. This, we're going to say 0 at ptnum. Oops, sorry. And that is going to act exactly like a blast, because we are removing all of the points. It's running over every point number, and we're just taking out the point. Now, if we wanted to do something like this, like 12, maybe 56. Now we're taking out point number 12 and point number 56 here, right? So this is how you could do it. You could also run it in a loop or some sort of control like that. All right, so removing a prim, very similar. Remove prim. However, this time we have to say what to do with the points, because obviously the prim has points attached to it. So in this case, we could say keep the primitives, right? And we could hit enter. And in this case, we should have it over primitives. And there we go. We have, that is interesting. Remove prim. Why is it doing it that way? Huh. Not sure why it's doing it that way. That is really odd. Let me just see if that's a, nope, not a viewport issue. Huh. I'm totally unsure of why it's doing it that way, but okay. We're removing primitives. We can also delete the points too by saying 1 is delete points, 0 is keep them. So basically, the question for this last argument here is, should we keep the points? If you write 1, or should we remove the points? If you do 1, yes, you should remove them. If you do 0, no, don't remove them. Great. All right. So one of the, oh, there we go. Duh. There's my reason why, because I'm using point number. Thank you. I'm sorry. Wasn't thinking straight there. Yeah. So obviously there's a good example of having to actually read your code and think about what you're doing. So yeah, there we go. That's why now it should work exactly the way we're expecting it to. It deletes all the primitives, but keeps the points. There we go. Great. But one really useful application for this is you doing like a random delete, right? So we'll do this in a primitive wrangle, and we'll just say if rand pt_num is less than a cutoff we're improving the wiki as we stream here. So cool. That's good. Yeah, element number. That's another one too, right? Yep. All right. Remove prim, and we're going to say 0 based on the @prim number. All right. And so we're going to add in a cutoff slider here. And now as we increase this, it's going to delete more and more until we're at 1. And the reason for this is that we're doing, we're creating a random number based on the current point number that we're looking at, which is actually interesting. You could also do this, I guess, with primnum as well, right? Should work. Yeah. So you could do that with either prim number or point number. Might make more sense in this case to do it with prim number because, well, whatever. So what it's doing with the random there, right, is it's giving us a value between 0 and 1 for each primitive or point, whichever you're using there. And if that is below the cutoff like threshold that you're setting here, then it's going to remove the primitive, which is the current primitive number, and we're also going to be removing the points as well. Looks like yes, we're also removing the points. So there we go. That's a kind of a random deletion little function there. what happens if you, okay, this is an interesting question. What happens if you invoke PT_num in a point wrangle? So, with a, yeah, prim wrangle. That's what I thought you meant. Okay. So in a prim wrangle, I believe what it's, because there's a certain number of points, right, that are connected to those primitives, right? So I know very obviously what happens the other way. So if you, in a point wrangle, if you call primnum, it'll find whatever primitive that point is attached to. I'm guessing that in the other way, and I don't know this for sure, but I'm thinking what it does is it takes the point that's associated with the first vertice. That would be my guess. So the first vertex point is going to be the one that it uses, I think. But I don't know that for sure. I'm kind of curious. Matt might know that better than I do. I mean, I don't know. I don't know everything. I try to preface my streams with that, where it's like, I'm not the expert on everything, but I'm pretty sure that that's how that works. If Matt doesn't have a good answer, I could probably ask that tomorrow at work. And there you go. Matt doesn't know the answer either. All right. So I don't feel quite so bad, but yes, cool. Well, thanks, Matt. I'm really not sure. That's an interesting one to test too, because I'm like trying to think of how, I guess there's ways you could do that, right, to be able to test it. Yeah. Anyways, it's kind of, I'm guessing that's what it is, but I don't know for sure. That certainly is an interesting question. So maybe Matt will have an answer for us in the not too distant future here. Thank you, Matt, by the way. That is very helpful. Yes. Yeah, that's what I think too. I think it's the first point in the winding order, which is the first vertex. So that's my guess as well. But I do not know definitively. But it clearly works, because in this case, it is actually giving us, there we go. We did it. First point. So there we go. Winding order. So, here you can see that this is telling us, like, in our geometry spreadsheet, what the first point is here. So this one, the first point number is 0. And in this one here, the first point is 2, and so on and so forth. So that would be what would be returned if you were calling that. It's based on the first vertex in the primitive. Cool. All right, well, let's do one more thing here before we move on, and that is adding in a seed to this random value. So what we can do is we can add another argument to this random function and put in a seed value here. And I think that was all that changed. Yes, I think so. So let's do that, and then we'll have a seed. And now we can get random random deletion of these primitives. So that's kind of another cool thing to add some randomness into your, whenever you're doing, trying to do something that looks more natural, you need to add in randomness, obviously. And controlling a seed value, you could do that, a bunch of different ways in your code, with a slider like this. There's a bunch of different ways that you could really control how to, have that seed for your random noise. So there we go. There's just some ideas about how to use something like remove primitive, remove point, things like that. So the last part of this day is talking a little bit about debugging. And we've done a little bit of this already. You've seen me do this live, which hopefully is helpful to see how maybe I go about doing that. But like what Matt says here is that you can feel amazing when everything works right and it's all doing the thing you want it to, but it can be a real annoyance to try to figure out why things aren't working, right? And I think when you think about what Vex is doing, I'm just going to maximize this real quick. When you think about what Vex is doing kind of from its, from a very basic standpoint, it's running this code over thousands of points many times, and just printing out that error, 40,000 times or whatever, is kind of going to be a mess, right? And another thing is that if you look into how multi-threaded programming works, which I will admit I know basically nothing about outside of Houdini, it's really tricky, right? There's a lot of things to deal with, and Vex kind of helps through that complexity. I know that if you've ever done any, I think it's OpenCL programming can be really tricky in a lot of ways because you have to worry about the threaded, multi-threaded nature of it, like kind of the multi-processing kind of that's going on there on a GPU, right? So, so here we have kind of a list of things that you can kind of like techniques and things to watch for and things like that can help you debug what's going on in your code. So let's just kind of go through these and we'll talk through them a little bit. So the first one is find the real error in a text wall of errors. So like what happens a lot of times because of that, we're running it over 40,000 copies and all that stuff. You can have this kind of boilerplate text at the top and it looks like a huge amount of text and there's kind of all these things that are happening in there. But a lot of times there's one error that'll start to stick out to you, and over time you'll realize like, oh, that's the error that I'm looking for because it's kind of different than the rest of this like boilerplate text that's kind of all just being spit out by the wrangle. And the one that Matt says is a key to watch out for is the undeclared variable. That is basically when you're trying to call a variable in your code and you haven't declared it anywhere. So that can happen. Chat verified, fooled them again. So that's one thing to keep an eye out for, right? Like finding that like real error in your big long list of errors. Another one is looking for missing brackets, right? I did that a couple times, once or twice today. And so there's a lot of brackets happening. And there's and since Vex is 3D, right, that means there's going to be lots of vectors and matrices, which, it's another day. But, you can get a syntax error and look for a while and then notice there's a closed bracket or a swapped bracket that should be curly versus, standard. So like one that Matt says he commonly misses is like with if statements where you're like saying if something, you're testing it against something and you forget to put your second close bracket at the end of it because you might have a channel in there or something like that. And it feels weird to put two brackets sometimes when you're just typing. So that's one that he says is really pretty common. So something to keep in mind, like your brackets are, you have to try to make sure that they're matched up. And there is highlighting too. If you're in Houdini and you hover over this bracket or you're right after this bracket, you can see it might be hard to see on the stream, but the initial bracket should show up as like a green dot around it. So it's a way to kind of see where your brackets, match up and how they're paired up. So another one is syntax error line number. So the error statements usually will give you a line and a column reference. So if you see that in your error, go to that place and look and find it, right? So that there's a little a text field down here that indicates where you are. So if you click down here, this changed to line 3, column 2, right? So there's also line numbers here as well. So lots of ways to see what your line that you're working on is and like what that error might be referring to. Yeah. Yes. That's another thing too. If you want to have your text more readable, you can do Control and plus. I did that once tonight to make it a little bit bigger. So yeah, you can keep increasing the size, till it's a ridiculous size as well. But there you go. You've got, you can also change that. If you're looking through it and you're like trying to make sure everything's, how many, where's my matching brackets or whatever, you can find that there as well. Nice little tidbit there. So then another one is the syntax error off by 1. So often the error will be a line after the real problem. Yes, for us old guys that have older eyes, it's a lot nicer to read text that's not maybe so tiny. So if you remember, I forgot to do a semicolon on one line, and the error came up on the line below. And so that's one thing to keep in mind too, that if you see a semicolon, you should look to the line. Like if it's saying the syntax is a semicolon, look at the line above and see if it's missing semicolon. Another one is the auto creation of attributes by mistake. So the coding languages, it says here, can be categorized as strict or not. Vex is like mildly strict, but wrangles aren't very strict at all. And so you can just write an at and then whatever you want after it, and it'll just make attributes for you, right? So one thing mentioned here is like you flip around DC instead of CD, and it'll just make an attribute called DC for you. It doesn't know it's a syntax error. It'll make that attribute and just kind of move on. And then you're like, well, why didn't it change my color? Oh, because I wrote DC instead of CD, whatever. So another thing is like using a variable like foo, float foo, and then start in your code at some point referring to at foo. Well, that's an attribute instead of a variable. So it's not wrong, but it's just going to make a variable foo that is going to be sort of nonsensical. And then can be hard to kind of track that down, see where that is in your code and kind of figure out what is actually happening there. Another thing to watch out for is not setting the data types on attributes. I mentioned this a little bit earlier in the stream today, that if you have a wrangle that defines like a vector here called like v at my call, and then later you use something like at my call, Vex doesn't really know what the data type is for that attribute. It only knows certain ones like P and C, D, V, blah, blah, blah. There's some that are like special attributes that it knows what those are going to be. So for the most time, they're basically just going to be treated as float, and it'll read in the first component, which is X, and it'll only read in the red channel of your color. So then you're like, why is this giving me like gray values or something like that? And like trying to figure it out. Because it's setting all of your components of your color to one thing or doing something with your noise that doesn't make any sense. So that can get really weird when you're doing that. So you should always get in a habit of using the data type prefix on your attributes. I don't think we've really gone over this. So let's take a look at this here. I'm just going to scale this up a little bit here. And on this page here, where is it? Sorry, let me just... I scroll by it. There it is. All right. So it's on this page. I'm going to drop this in chat here. So these are the Vex types and their syntax, right? So if you do float, it's F. A 2 float vector is U. 3 float is V. 4 float is P, which is weird. I think it'd be Q for quaternion, but it's P. Don't know why that is. Maybe somebody knows. I don't know why. Int is I, and then there's things down here for matrices. So if you got a matrix 2, it's a 2. Matrix 3 is 3. Matrix 4 is 4. And then other common ones, S for string, and a little less common, D for dict or dictionary. So these are all things to keep in mind when you're reading in your attributes, to write F at whatever or U at whatever, so that it'll read it in. Now, if it's a float, you can just do F, or you don't have to do F and it'll read it in as a float. However, it's good to get in the practice of that, because a lot of times you might read in an integer attribute that you want to be an integer and read it as a float. That could cause issues down in your code somewhere if you're running a function on it or something. There could be issues that arise from that. Same thing with, obviously, we mentioned vectors and stuff like that. So keep these in mind and keep these handy, so like, oh, I need to make if you need to make a vector 4, use P at and then give it your name. So that's a really handy thing. And Matt admits that he's not in that habit as well as he would like to be. So yeah, so it's a good thing to get in a habit of, and make sure that doesn't cause you any problems. And then the last one is just equal signs can be tricky, right? We talked about that a little bit before. A single equals an assignment. A double equals is kind of a comparison for equality, kind of a question, right? Is this equal? A plus something is add something to the variable. So when you're typing quickly, you could very easily think, oh, I'm doing this, but then you just do a single equals And Matt says you go into a rage for 20 minutes trying to understand why your code isn't working. So oftentimes a good place to check if you've got a lot of equals and things like that you're doing in there, or checking equalities or adding something to variables, just go back and make sure that you didn't miss a plus equals or a times equals, or flip one of them, right? You might have done a times equals instead of a plus equals, things like that. So check those things out and see, what works, what maybe might be wrong in your code. So those are just some ideas of how to go through and debug your code. And it's not an exhaustive list, but it certainly is super helpful to kind of start to frame your mind on how those things work. So that's day 14 there of the Joy of Vex. And so if you guys have any questions about what we're just talking about there, it's always great to see, people dropping their questions in chat as we're going. That's awesome. We can kind of make corrections as we go. If you have any more on this day's topics, throw them in chat. I'm going to talk over the exercises a little bit as we're going here. And if you guys have any questions or comments, we'll tackle them as we go. All right. So the first one is the seaweed example doesn't lock the roots in place. So fix that. So I'm just going to slide this over to the side again here and bring this down a little bit here. I don't know if this is. I think we'll do it like that. That's probably okay scale. So when we're doing this seaweed example, right? If you look closely, the roots are actually moving around. So they're not locked in place. So what we need to do is we need to take the offset and make sure that it's at 0 at the beginning of the loop, and then gradually ramp it up so there's a larger and larger effect till the end. So what his hint is, if only there's some sort of counter starting at 0 that you could multiply by a small fraction that you could use for this, that would probably be helpful. So think about that, and that can help you lock those roots in place. Make the seaweed move in very computery circles. Offset them slightly from each other. So the GIF and answer are below. Look at the GIF first. Try to avoid the code. And the hint is you'll be moving each point's X and Z position based on sine and cosine. So if you have sine and cosine, you can make circular motion together. It's really nice. Color the lines from root to tip somehow. There's probably a way to do that, right? Take the stochastic slider based prim delete example from above, change its point mode to a point wrangle, and make it remove points instead. So I actually think I might have done that in the stream at one point, or something. Well, no, I just showed how to remove points, but yeah. So instead of doing this here with primitives, do it with points instead. I do that. I've done that quite a bit with different effects and things like that, removing points and doing that as an effect maybe moves along something. So, and then last, rand is pure white noise static. Sometimes you want a more structured, want more structure for this delete trick, right? So try and make the delete work based on noise. So noise doesn't take a seed variable, but you probably want controls that'll scale the size of the noise, offset it, maybe animate the noise over time. So you could have like noise like flowing across a grid or something like that to delete based on that. So that is another option as well. So there we are. There we have it. Day 14 of the Joy of Vex. So yeah, thank you guys all for following along with this tonight. It's always great to have people in chat and talking through this stuff so that we can get this content to be as good as possible, right? So that we're making sure that it's clear and understandable, right? So if you guys want to connect with me throughout the week, or give suggestions for stream topics in the future, we've been doing this, it feels like for like a couple months now, but it's like a week and a half that we've been doing this Joy of Vex stuff. Or maybe it's like 2 weeks, but anyways, In the future, we'll be doing streams on other topics, right? So if you have topic suggestions, you can throw them into the Discord server. I have a little forum kind of thing channel made up. So that's a great place to get some feedback on what you'd like to learn about or see. There's also places there for help and things like that. So if you're running into any problems with this stuff, you can certainly throw that in there as well. You're very welcome. Thank you for watching the stream. So you can go to Houdini Hangout, get a Discord server invite, and do that. Again, huge thanks to Matt for being here to have some comments and redirect my brain when I was forgetting what difference between primnum and pointnum and different things like that are. And the cgwiki is super, super helpful for not just Vex stuff, but I mean, there is a ton of stuff on here, tons of Houdini content, crazy amounts of stuff, lots of great things that'll help you maybe when you're stuck, things that'll help you with maybe new ideas for things, lots of examples, lots of GIFs, really, really helpful. And shoot Matt a little donation if you're finding yourself using it a lot, because it's super helpful. And there's even stuff in here about USD guide. It's like the Joy of Vex for USD. So, if you're looking to get into other things, maybe that you've never even touched before, Matt's put a ton of his learning online for us so that we can then learn along with him. So huge thanks to that. And hopefully you shoot him a little donation for his extensive efforts for the community. That's it for me for tonight. Thank you again for watching. I'll be streaming the next 3 days content on Wednesday. So we'll be doing Wednesday, 8 p.m. Eastern time. Sorry if that hits a weird time for you. Do my best to make sure that this is at a reasonable time, but there's choices that have to be made. If you can't follow us live at 8 o'clock Eastern time, again, this Saturday, I'll be doing a 1 p.m. stream Eastern time, which will be a lot better for people in Europe and maybe in other parts of the world. So, we had people from Africa that joined our stream, which was really cool, from Angola, I believe. So it was really neat to see some people from different parts of the world. So that might be a thing I do more often, just because it was kind of neat to be able to interact with some new people. So that is it for tonight. Thank you again for watching, and I will see you next time. Bye.